One of the most famous ideas in quantum mechanics is superposition. The idea that a quantum state can exist as a combination of multiple possible states. This concept is often described in strange or philosophical ways, but in reality, it comes directly from the mathematics of the theory. In this video, I'm going to explain what superposition actually means, why it appears in quantum mechanics, and how it shows up in real physical systems. To start, let's look at how quantum mechanics describes physical states compared to classical physics. Before talking about superposition directly, it helps to compare how classical and quantum physics describe physical systems. In classical physics, systems have definite states. A particle has one position, one velocity, and one value for any measurable quantity at a given time. If we don't know that value, the uncertainty simply reflects a lack of information. Quantum mechanics describes systems very differently. Instead of definite values, a system is described by a state vector in a Hilbert space. This state can be written as a linear combination of basis states, and the coefficients of that combination determine the probabilities of different measurement outcomes. The mathematical structure is what leads directly to the principle of superposition. Superposition comes directly from the mathematical structure of quantum mechanics. A general quantum state can be written as a sum of basis states, each multiplied by a complex coefficient. These coefficients determine the probabilities of different measurement outcomes, and they must satisfy a normalization condition so the total probability equals 1. The reason this works is that the Schrödinger equation is linear in the state vector. Because of this linearity, if two states are valid solutions, then any linear combination of them is also a valid state. A simple example of superposition appears in a spin 1/2 system. The Hilbert space for spin 1/2 is two-dimensional, meaning there are two basis states, spin up and spin down, along a chosen axis. Any quantum state can be written as a linear combination of these two basis states. The coefficients in that combination determine the probabilities of measuring each outcome, and they must satisfy the normalization condition so that the total probability equals 1. When we measure a physical quantity in quantum mechanics, the measurement operator has a set of eigenstates. For example, if we measure spin along the z-axis, the eigenstates are the spin up and spin down states. If the system is in a superposition of these states, the measurement does not reveal a hidden value. Instead, the state collapses to one of the eigenstates. The probability of each outcome is determined by the square magnitude of the corresponding coefficient in the superposition. Another important idea is that superposition depends on the basis we choose. For example, a particle that is spin up along the x-axis can be written as an equal superposition of the spin up and spin down along the z-axis. This means that a state which is definite in one basis may appear as a superposition when expressed in another basis. In other words, superposition is not just a property of the system itself. It depends on the basis used to describe it. Superposition is not just a mathematical idea. It produces real physical effects. In the double slit experiment, interference patterns appear because probability amplitudes combine before we calculate probabilities. The same principle explains atomic orbitals, which are superpositions of wave functions. It also forms the basis of quantum computing, where qubits use controlled superposition of two states. The key idea is that superposition is not a strange extra rule of quantum mechanics. It comes directly from the mathematical structure of the theory. Quantum states are vectors in a vector space, and the Schrödinger equation is linear. Because of this linearity, linear combinations of valid states are also valid states. Measurements then select one of the eigenstates, with probabilities determined by the coefficient of the superposition.